So in this afternoon session, we'll be doing 2D lake model, and it will be a hands-on problem. So first I'll explain what we're going to do as I did yesterday. So this would be a good exercise for you to bring in real time series and assign different boundaries. So the outline is we'll be building 2D model and slicing and dicing and looking at different features within EFDC Explorer to view our models. So we were using the same study area where we created a bitmap georeference map this morning. And so for this example, we'll use a Cartesian grid because it's a lake. There's nothing really meandering, or you don't need to use a Cartesian curvilinear grid on this example. So we're just going to use Cartesian grid. So we have provided a shoreline and bathymetry data that we're going to use, and all of those files are in the projects folder. So we'll run the model for hydrodynamics, and then we will add salinity, temperature, depending on how much time we would have, and it will be a hands-on. So this is the study area. All of you already saw it before in Google Earth. So the data was derived from University of South Florida's website, and they have this contour maps, and we digitized those bathymetry and extracted the X, Y, and Z coordinates that we will use to define the bathymetry. So this is a typical P2D format that I have been talking a lot about. So what happens is each sets of points will have a name. For example, Z8, it means coordinates with a elevation of 8. So it can be like 1,000 rows, and we can have one name for that particular for those rows. So it's like every time you end this sequence of rows, then you will end with an asterisk, then you will start with a new name. So that would be an identifier, and when you are referring to G12A, then it will be reading all the files between that label and the asterisk that follows. So we'll be building 2D grid. We'll be using a shoreline bathymetry and a shoreline file, and then assign bathymetry. Next step to EFDC Explorer 8.3. This is 8.0. So again, we'll use the same button to create a new grid. This time we'll use a different function. We'll bring in polygon so we can clip whatever we don't need. It will be more clear when you go through this. Then we'll bring bathymetry. So this is the EFDC data structure. So if you decide to go dive into code, you will see a lot of A of L comma K. A is a typical arrays that you have. For example, if you have AH, that's a horizontal momentum diffusion. So it will be AH L comma K. So each cell will have individual values. So I here is a pseudo X, so it's not a real X, but it's the grid uses I and J to distinguish the direction. K is the vertical layer, so if you have 10 layers, the value of K would be 10. And L values are stored in the memory with I and J index for each cell. So if you say L of 5,7 or L equals 3, it might be referring to the same cell. So two indices are merged together into a single index, so it's easier to identify when you're running a lot of loops, so you don't have to refer to I and J every time. So that's the basic code, how the code is implemented behind the scene. After you have created the grid, you can look at it into your view plan. So when you look into cell map, it will always show like X and Y direction. Even if it was curvilinear, it will still show straight. These are the L index, I and J index for those particular cell. You can choose how many to skip. So go over it later. Then what we do is save our model. Then we'll assign initial and boundary conditions. So in order to assign initial, it is the same button that we use. Go to domain, initial condition, and bottom roughness. For bathymetry, we have a data file today, so we're not going to use a constant value. So we will import a data file, and that's the bath file that we'll be using. So after you have specified bathymetry, your bathymetry will look like this. It's not nowhere constant, or there is no slope. It's real data. Then we are specifying the water surface elevation of 11.5, and that number is the initial condition. You always have to do trial and error method to figure out whether you have all the cells are wet or not. So initial condition will quickly change. It may not have a huge impact, but in a bigger study areas, it's people usually do like spin up periods. You run the model with a boundary condition for 7 days or so, or even a month, depending on what type of model you use. And after that, it will kind of stabilize, and different constituents will have a different concentration at different regions, so you will have a reasonable starting point. So spin up is usually done to have a good initial condition. For simple examples like this, you wouldn't need to run up spin ups. Then we'll go to boundary condition, assign flows. So this example will have just one inflow and one outflow, and we'll explore different features. So here we'll use the feature import data. So if you have different formats of data, you can import it using this import data. If you decide, you can just copy and paste from Excel or any other software. And this is the file we'll be using for initial inflow and outflow. We'll use the same button. We have provided you the files that has date time stamp and the values for inflows and outflows. So if you just want to copy and paste from Notepad, it will look like this. So these are the inflow and outflow of the lake. So we'll assign the location for inflow and outflow. Create a new boundary by using new. When you're in the boundary condition viewing option, then both of them will be the flow boundary. So you'll use one, and again go to your flow assignment window and assign the inflows. Then create a boundary condition for the outflow. It will be the same type, so 1. So you assign your outflow boundary here. Factor is like if you have a boundary group and there are like multiple cells in that group, but if you want to use just one time series, then you have to divide how the flow want to contribute to the system. So 10, let's say 10 cells, right? So you can decide to have 0.1 factor for all the cells, so the total would be 1. If you're not sure, you can tell you can use this button, and then it will distribute based on the size of the grid cells. So if they are not constant, some cell will be like 2 times bigger than the adjacent cell, and you would think that that cell should contribute more than the adjacent cell, and that should be the good thing to do. So I would use a distribute factor here if I have multiple number of grid cells in a boundary group. So how would you know that you have multiple grid cells? So if you have multiple grid cells, right now it says current cell 1. So if you had like 10, it will have 10, and this button you could be able to scroll and go over different points. So if you want to remove any particular location, you could just add or click on add cell or remove cell from there, and you could easily add or remove cell from the boundary group. And wetting and drying. For this example, we don't need wetting and drying because we know that these cells will always be wet and dry, but just wanted to show you how I would by default choose my model to have wetting and drying, so just in case if I'm working on an estuary or some other areas where there will be flows coming into the system in some season, and there will be dry flow, or there will be no flow, so some of the cells might become dry. So if you do not activate wetting and drying, you would end up having negative depths. So it's always a good thing to activate wetting and drying. So when you're working with these kind of dynamic systems, you will have to use horizontal diffusion model. So EFDC has horizontal momentum diffusion with Smagorinsky option, and you would have to provide this eddy viscosity in horizontal and Smagorinsky coefficient. Usually we derive this initial eddy viscosity by looking at your cell area. In EE, you go to cell statistics, and it will give you minimum cell size and minimum cell size in X direction and Y direction. That's how you find out the minimum cell area of your overall domain, and then you divide by 10,000 to get a rough number to start with. You can play around with that number, and that will change with the grid size. So if you have a really coarse grid size, that will you would have to use a bigger number. But if you have really coarse size, that will probably go into 0.1 or 0.01 something. So it's just for numerical stability. And the value of this momentum diffusion coefficient, it ranges from 0.1 to 0.25 typically, but I've seen people using 1 also. Not sure what their logic is, but if you look into literature and documentation, it's usually from 0.1 to 0.25. So then I'll show you the model metrics, where you can see it will give you a rough idea about what should be your initial start of delta T. So here it's a CFL time. It calculates the CFL time based on the your depth and your initial condition, and it ranges from 5.4 to 13.69. So you would somehow find like the value somewhere in the middle, and then start your model run. You don't want to try like 0.1 or 1 at first, because it will take a lot of time. So it would be a good guide for you. So then we will assign the initial start time and how long you want to run the model, and duration will still use the 24-hour duration. So the time step we chose was 10 seconds. It was between 5 and 13, so we'd run 10 seconds. You could try 12 or so. It should still run. If it does not, you can lower it time step. So most of the time when your model crashes, you might want to check your time step. EFDC Explorer linkage, this time we're going to output every hour. You could choose to output every 2 hours or 3 hours. For this example, we are not going to compare with the real data, observed data. We're just going to run the model and explore different post-processing features. Then we'll assign. Usually you don't have to check these executables once you have provided the right executable, but I just want to make sure every time, because when you have different versions lying around, it's hard to tell which model, which executable that you used. And then we'll run the model, let it run, and then we'll look at velocity distribution or some other constituents. So we can extract the velocities from. You can either extract magnitude and direction, or x and y components of velocity. And if you have more than one layer, then you can extract velocities for different layers. And if you check depth average, it will give you the depth average. Then next thing we will do, if you have time, we'll activate salinity. So the only thing you do after you activate any new parameter, the first thing you need to do is assign the initial conditions. Usually it's 0, unless you're working on an estuary where your salt water should be somewhere around 30 to 34, and your fresh water should be around 0 to 4 or 5. But this is a simple example. We'll just assign 0 to we're going to use 0.2, and upstream we have 0.5 salinity. It's really low, but the purpose of this example is to show how to implement the salinity. Usually if you have really less than 1, you don't even have to simulate salinity because it's not going to impact a lot, unless there is a big event or hurricane that can pull water from way downstream to your study area, but that would be a sensitivity study. So then we specify the salinity boundary condition only to the inflow, because outflow we don't need to specify the concentration, because the outflow concentration will always be from inside the domain, so nothing is coming in from outflow, so we don't have to specify the concentration for outflow. So that's how after we define the series, then we tie it to the boundary condition. So in this case inflow, so we'll choose this salinity and the series that we defined earlier. Next we are going to add wind into our system and see how wind impacts our results. So you could make 2 different runs, one with wind and one without wind, and look at velocities or water surface elevation. Then you can see the impact of wind. So we have provided the wind data, and I just copied and pasted from that spreadsheet or that file. And then run the model, you can see your timing frames. So these are timing frames where you can see the hydrographs for inflows and outflows. Essentially it's a hydrograph that is inverted for the outflow, so whatever is coming in, it will go out, but there will be a slight time lag from when it goes from here to there. And we also included wind here to see which direction wind was flowing in each time step. Next we'll activate temperature. So for temperature in EFDC model we have several options, like we have 5 options now. In the original EFDC we had I think 3. So DSI added equilibrium temperature concept, that's from C equal W2, and there is another new method that was added recently, that's fully balanced with variable extinction coefficients. So we're going, for this example we'll just use this equilibrium method. So if you were to simulate ice into your system, there is a separate tab here which says bed heat and ice options. Then there is option you can turn on and off. And based on your solar radiation, air temperature, and other atmospheric parameters, if it's really cold, and the model will automatically create ice, and you can view the ice into your domain. So we will add boundary condition for temperature and the atmospheric conditions. Just copy and paste it. Then assign the temperature for the inflows. So when you have this atmospheric time series, you need to specify latitude, longitude, and the one important parameter is you either have wet bulb temperature or relative humidity. So most of the times you have relative humidity, so you need to specify one value here. On the prior versions, when you click on show parameters, it will be slightly different, but this option should be available on the prior versions if you are using EE 8.0 or 8.1. Cloud cover? Yeah. I mean, sometimes we do, sometimes we don't, but I think we had, while at Auburn, we had this program that will calculate cloud cover based on this solar radiation and some other factor. So, yeah. That's not available online or anything? I mean, yeah, it was available for most of the stations. For like Mesonet station, you could go AWIS.org and see if there is a location where you have your cloud cover. And usually these regional airports, they have cloud cover, but some of them they don't have solar radiation. Yeah. So it's always tricky to find all the data.
Yeah.
EFDC Explorer has an option to, if you don't have a solar radiation, you can tell the model to calculate the solar radiation itself.
Okay.
So it will compute the solar radiation for you, but it's nowhere close to the measured data, right?
It's better to have.
Yeah, better. Yeah.
Yeah.
So if you don't have that, then there is an option
Yeah.
to use in EFDC Explorer. Again, after we have assigned the boundary condition time series, we'll tie it to our boundary groups. Then, so far we had only one layer. Now we want to change to 5 layers. It's easy. Go to domain, grid. You just specify how many layers you want. Hit enter, and then it automatically changes your model to 5-layer model. Then if you go back to your boundary condition and look at your inflows, it will now have 5 layers instead of 1. So everything is taken care of by EFDC model. And then you say like, oh, I made a mistake, I want to change back to 1 layer, then you hit 1 layer and it will convert back to 1. So it's easier to have 1 layer or 5 layer, whatever layer you want. And if you want to use Sigma Z model, not the regular Sigma. So the basic difference between Sigma Z and Sigma is, in Sigma stretch, we say Sigma stretch, so every cell would have same number of layers in Sigma, regardless it's this much shallow or if it's this much deep. But in Sigma Z, what happens is you can have 2 layers on this shallow region and like 20 layers on this deeper region. So if you're working on lake, I would recommend using the Sigma Z model instead of Sigma, unless it has more or less same bathymetry. But I suppose there would be some regions where they will be much deeper than others. So that's how you determine which system you want to use. So if there is a lot of stratification in the system, I would definitely use Sigma Z. So that reduces artificial mixing error that we have in traditional this kind of vertical Sigma stretch models. So after I have run the temperature and I was looking at this bottom layer, you can overlay velocities on top of your temperature, so you can see what velocity is doing and what is the temperature at that particular time. So you can see both direction. So there is a circulation pattern going on, and you can see in the middle you have a lower temperature, and there is a higher temperature at the banks because they are shallow and it gets heated up quickly. Dye, we could add dye. It's the same approach. We revert back to 1 layer, or you could just keep 5 layers and assign 5 values for your boundary condition. So we're going to use a dye with a decay rate of 0. So you assign by dye boundary condition, then tie it to your location that you have defined in the model. Then you can see what is the flow coming in from here and how long would it take to reach that particular location. And you could even have a line created, like a polyline from here to here, and see each distance how it is changing. And we can create an animation. I think we'll play around that. Then we'll use some other features how you can extract results from this model.